Nature is a master engineer. Over billions of years, it has crafted intricate solutions to complex problems. We can find these solutions everywhere. Take, for example, the effortless flight of birds or the efficient swimming of fish. Scientists and engineers are turning to nature for inspiration. This field of biomimicry has led to incredible innovations. One exciting area is nature-inspired micromachines. These tiny machines mimic the movement of living organisms. Imagine tiny robots that can swim through your bloodstream. This is the promise of nature-inspired micromachines. They have the potential to revolutionize various fields. Fasten your seatbelts as we embark on a journey into the world of nature-inspired micromachines. Before we can understand BZ-powered micromachines, we need to understand the fascinating chemical reaction that drives them. The Belousov-Zhabotinsky BZ reaction is a prime example of a chemical oscillator. Imagine a clock that uses oscillating chemical concentrations to keep time. That's essentially what the BZ reaction does. In a BZ reaction, specific chemicals undergo a series of reactions. These reactions cause the concentration of certain components to rise and fall periodically. This creates visually stunning patterns. Imagine a liquid that spontaneously changes color, oscillating between clear, yellow, and blue. This is the mesmerizing dance of the BZ reaction. The BZ reaction is not just a chemical curiosity, it's a powerful tool for understanding complex systems. It serves as a model for various natural phenomena. These include the beating of the heart and the rhythmic firing of neurons. By studying the BZ reaction, we gain insights into the fundamental principles governing these biological processes. But how does this relate to micromachines? Well, imagine harnessing this oscillating chemical energy to power tiny machines. That's precisely what researchers have achieved with BZ-powered micromachines. By strategically incorporating catalytic materials, they can control and direct the energy from the BZ reaction to propel these tiny devices. The key to harnessing the BZ reaction for propulsion lies in the use of catalysts. Catalysts are substances that speed up chemical reactions without being consumed themselves. Think of them as facilitators, enabling the reaction to occur more efficiently. In BZ-powered micromachines, catalytic materials are strategically placed on the surface of the particles. These particles are typically made of materials like polymers or silica. The catalytic patches create local variations in the BZ reaction rate. This asymmetry generates a chemical gradient, much like a slope in a landscape. This chemical gradient is the driving force behind the self-propelled motion. The particles move from areas of high reaction rate to areas of low reaction rate. Imagine a surfer riding a wave. Similarly, these micromachines surf the chemical waves generated by the BZ reaction. The choice of catalytic material dictates the direction and speed of movement. By carefully selecting and positioning these catalytic patches, scientists can precisely control the motion of these microscopic machines. It's like programming a tiny robot with chemical instructions. One of the most remarkable aspects of BZ-powered micromachines is their scalability. Scientists have successfully created these self-propelled particles at various sizes. These range from the macroscopic millimeter scale down to the nanoscale, where objects are measured in billionths of a meter. At the millimeter scale, these particles are visible to the naked eye. They resemble tiny, pulsating beads, moving erratically in a chemical solution. These larger particles are ideal for studying the fundamental principles of BZ-driven motion. They provide a visual and measurable demonstration of this fascinating phenomenon. As we move down to the microscale, the particles become invisible without a microscope. But their potential applications in fields like medicine and robotics become even more apparent. Imagine tiny robots that can navigate through blood vessels, delivering drugs directly to diseased cells. This is the promise of microscale BZ-powered machines. Further down the size spectrum, we enter the realm of nanotechnology. Nanoscale BZ-powered particles, or nanobots, hold immense potential for targeted drug delivery and cellular repair. These tiny machines could revolutionize medicine, offering precise and minimally invasive treatments for a wide range of diseases. Section 5. Mechanisms of motion surfing chemical gradients. The movement of BZ-powered particles is a fascinating interplay of chemistry and fluid dynamics. These particles don't have propellers or fins like macroscopic machines. Instead, they rely on subtle interactions with their chemical environment to generate motion. One of the primary mechanisms driving their movement is diffusiophoresis. This phenomenon occurs when a chemical gradient creates a difference in the concentration of molecules around the particle. This difference in concentration leads to a net force that propels the particle. Imagine a boat on a still lake. If you drop a small amount of soap at the back of the boat, it creates a gradient in surface tension. This gradient propels the boat forward, even without any wind or oars. Similarly, BZ-powered particles exploit chemical gradients to achieve self-propulsion. Another mechanism at play is chemotaxis. This is the ability of organisms to move towards or away from chemical stimuli. Bacteria, for example, use chemotaxis to find food sources or avoid toxins. BZ-powered particles exhibit a form of chemotaxis, moving in response to the chemical waves generated by the BZ reaction. Section 6. Swarming behavior, strength in numbers. In nature, collective behavior is often the key to survival. Schools of fish, flocks of birds, and ant colonies all exhibit remarkable coordination and efficiency. This swarming behavior allows them to achieve feats that would be impossible for individuals. BZ-powered micromachines also display emergent swarming behavior under certain conditions. When a large number of these particles interact, they can spontaneously organize into patterns and move collectively. This behavior arises from the interplay of chemical gradients and hydrodynamic interactions between the particles. Imagine a group of boats, each creating its own small wake. When these boats are close together, their wakes interfere with each other, creating complex patterns of waves. Similarly, BZ-powered particles influence each other's chemical environment, leading to emergent collective motion. This swarming behavior has significant implications for potential applications. Imagine a swarm of microscopic robots working together to deliver drugs to a tumor or clean up an oil spill. The collective effort of these tiny machines could amplify their impact and efficiency. Section 7. Chemical sensors sniffing out the environment. Our sense of smell allows us to detect and respond to a wide range of chemical cues in our environment. From the sweet aroma of freshly baked bread to the pungent odor of spoiled food, our noses provide valuable information about our surroundings. BZ-powered micromachines can be engineered to function as highly sensitive chemical sensors. By incorporating specific receptors onto their surface, these particles can detect and respond to the presence of specific molecules. These molecules could be pollutants in the environment, toxins in the body, or even markers of disease. Imagine a network of microscopic sensors deployed in a river to monitor water quality. These sensors could detect minute traces of pollutants, providing early warning of contamination. Or envision tiny robots patrolling your bloodstream, identifying and neutralizing harmful substances before they can cause damage. The sensitivity and selectivity of these chemical sensors can be tailored by modifying the receptors on their surface. This allows scientists to design custom-made sensors for a wide range of applications, from environmental monitoring to medical diagnostics. Section 8. Targeted drug delivery, microscopic couriers. One of the most promising applications of BZ-powered micromachines is in the field of targeted drug delivery. Traditional drug delivery methods often suffer from limitations. These include systemic side effects and inefficient delivery to the target site. Imagine a fleet of microscopic couriers, each carrying a payload of drugs, navigating through the bloodstream directly to the site of disease. This is the vision of targeted drug delivery using BZ-powered micromachines. These particles can be loaded with drugs or other therapeutic agents. Their surface can be modified with targeting molecules that bind specifically to receptors on disease cells. This ensures that the drugs are delivered precisely where they are needed, minimizing side effects and maximizing therapeutic efficacy. The self-propelled nature of these particles allows them to overcome biological barriers that hinder traditional drug delivery methods. For example, they can penetrate dense tissues, cross the blood-brain barrier, and even target intracellular compartments. Section 9. Navigating complex fluids, a microfluidic maze. The human body is a complex and dynamic environment filled with fluids of varying viscosities and intricate networks of channels. Navigating this microfluidic maze presents a significant challenge for drug delivery and other biomedical applications. BZ-powered micromachines are uniquely suited to operate in these complex fluid environments. Their small size allows them to maneuver through narrow channels and capillaries. Their self-propelled motion provides the necessary thrust to overcome viscous drag and fluid flow. Imagine a tiny submarine navigating through a network of underwater caves. The submarine's propellers allow it to move independently of the currents and explore the intricate caverns. Similarly, BZ-powered micromachines can navigate the complex microfluidic networks of the body, reaching their target destinations with precision. Scientists are developing strategies to further enhance the navigation capabilities of these particles. These include external guidance mechanisms, such as magnetic fields or acoustic waves, and biomimetic designs inspired by the movement of bacteria and other microorganisms.